Looking at the facts, it's an unusually cold region in the cosmic microwave background, 70 microkelvin colder than average, located in Eridanus. The supervoid explanation is disputed, and exotic ideas like universe collisions remain unproven. I need to avoid any invented details and stick strictly to these points. The anomaly first flickered to life on a monitor in 2004. Data from NASA's WMAP satellite streamed across the screen. A team at Princeton, scanning the universe's afterglow, saw it, a patch of sky significantly cooler than the rest. Not a star, not a galaxy cluster. Something in the oldest light itself, 380,000 years after the Big Bang. It lingered on the screen, a silent anomaly against the background hum of cosmic radiation. Planck satellite data confirmed it in 2013. The cold spot wasn't a blip. It was a vast region, stretching across 300 million light-years of space. Smaller cold spots happen all the time. This one was too large, too deep. Imagine a city block of ice in a desert of boiling water. Its temperature deviation defied standard models of cosmic inflation. Astronomers scratched their heads. What could cause such a deep chill in the universe's first light? The supervoid theory emerged. A giant void, a region with far fewer galaxies, might explain it. Less matter means less gravitational pull to heat the CMB. Studies map this void in Eridanus, but its size and density remain debated. Does it truly account for the cold spot? Some studies say no. The void's effect is smaller than needed. Others argue it's the best explanation so far. The void feels like a clue, but not a solution. The mystery deepens. Statistical fluctuations could create a cold spot this large, though the odds are low. For now, the cold spot sits in the cosmic record, a persistent question mark. The void might be a red herring. The universe might hold stranger secrets. But for astronomers, it's not a collision with another universe. It's a cold spot, 70 microkelvin in the oldest light, waiting for a clearer answer. The cold spot is a precise measurement, 70 microkelvin colder than the cosmic microwave background's average temperature. It sits in the constellation Eridanus, a region mapped by WMAP in 2004, confirmed later by Planck. Imagine a patch of sky where the universe's oldest light, released 380,000 years after the Big Bang, is measurably cooler. This isn't a small anomaly. It stretches across 1.8 billion light-years, larger than any typical fluctuation predicted by standard models. Astronomers proposed a supervoid, a vast region with far fewer galaxies, as the cause. Less matter means weaker gravitational lensing, potentially cooling the CMB passing through. Studies map this void in Eridanus, but its density and size are contested. One leading theory estimates its effect would only account for half the observed cold spot. The void feels like a suspect, but it's missing key evidence. Its gravitational influence falls short of what's needed to explain the temperature drop. Statistical flukes remain a possibility. The universe is vast, and such a cold region could theoretically arise by random chance. But the odds are low, like finding a single grain of sand in a desert the size of a continent. Some analyses suggest the cold spot might be a statistical outlier, a rare but not impossible event in the cosmic fabric. Yet for every statistical explanation, the cold spot persists as a persistent anomaly, larger and colder than expected. Exotic ideas, such as a collision with another universe, capture headlines but lack evidence. Astronomers have found no supporting signatures in the CMB or galaxy distributions. This cold spot is not a cosmic fingerprint of a parallel universe. It's a measurable dip in the oldest light, a puzzle wrapped in precise data. For now, the supervoid remains the most plausible explanation, though incomplete. The void might be a clue, but not the answer. The universe holds its breath, waiting for clearer observations to resolve the anomaly. The supervoid proposed as the cause stretches hundreds of millions of light-years across, a vast emptiness where galaxies are scarce. Yet astronomers measuring its density find it lacks the sheer mass needed to cool the CMB by 70 microkelvin. It's like finding a whisper in a hurricane, too faint to explain the deep chill. Current surveys show the void's density is about 10% lower than average, but gravitational models require a 50% deficit to match the cold spot's depth. The physics simply doesn't add up. Statistical flukes remain possible, though the odds are staggering. Imagine searching for one specific grain of sand scattered across a desert covering all of Europe, from the Alps to the Ural Mountains. Astronomers calculate the probability of a cold spot this size and depth arising randomly is less than 1 in 100,000. Such anomalies do happen in a universe as immense as ours, but this one sits too perfectly at the edge of statistical expectation. It's not a statistical error. It's a persistent, measurable anomaly that demands explanation beyond chance. Exotic theories, like the cold spot being a scar from a collision with another universe, dominate headlines, but no evidence supports them. Detailed maps from Planck and ground-based telescopes show no gravitational lensing signatures, no temperature patterns, no galaxy distortions matching collision models. The universe shows no sign of a neighboring cosmos brushing against it. This is not a cosmic fingerprint. It's a dip in ancient light, measurable and isolated. What would settle this? Precise mapping of the supervoid's mass through gravitational lensing. Future telescopes must track how light from distant galaxies bends around the void, revealing its true density. Only then can we confirm if it's the culprit or merely a coincidence. Until that data arrives, the cold spot remains a shadow on the oldest light, a puzzle where the simplest answer still feels incomplete. Is this a flaw in the fabric or just the universe's quietest whisper?